prepared. The basic purpose of our system is to bridge the communication gap between people who don't understand American Sign Language and people who are deaf and mute. We can enhance the system for use in cafeterias, ticket counters, etc. The gesture can be recognized by the machine to cater to the needs of the person using the system.
Bam, done. Perfect. So the first step in using our Kinect system is to calibrate the camera, which you see up here. And to do that, it uses a checkerboard, which is on the table. You can see it on the screen. And all you have to do is just click calibrate the checkerboard, pops up in the center of the screen, and then click OK. It happens pretty quickly and just says finish calibration. So the second step to running our Kinect system involves going into the Nimble SDK folder and running a command to run it. And that enables us to hand calibrate now. Okay. Alright, so now we're just showing you the actual hand calibration part. Very bottom left, or right for the camera, I guess. It shows the two hands, one in red and one in blue.
You can see the actual detection of the hand.
So you can see the actual detection of the hand in the blue and the white, blue, red, and the white. And the different, you can see the rendering of his hand doing the different signals. So the last part of the second step is to make sure that you keep the window open for the hand calibration. And that brings us to the third step, which is to run the draw skeleton Java file. And that brings up what you see here with the grid that shows the two different hands. As you can see in the background, that show the hands in a three-dimensional grid. Our Kinect application titled KiGest. In the bottom left, you see the version number. This is our communication tab where you'll see this is where the hand signals will be inputted, so this is sphere. And then, well, so first you hit start, you show the motion. You show the motion. After you're done, you hit stop, and the output is displayed at the bottom. Next tab is for lookup, and this just helps people who don't know all the words or want to look something up. So acid is an example. Lots of words in the dictionary for this. Raccoon. And then our last tab is the help tab, and this is just for error reports or if they have any questions or customer support. With the confirmation that it sends, and that is the user interface.
Okay, so I'm going to explain the code for pre-processing for the gesture accept. So we get the output accept 1_left and output accept 1_right.txt, these two text files from the input gesture that we showed to Kinect. And these text files contain the coordinates of hand motion for 5 fingers and the wrist and our centroid. So I just gave it as the input to input left and input right, and then these are just separated into different arrays, and then these are written in F1. Left means finger 1 left, finger 2 left, 3, 4, 5, and the same goes to centroid, right, wrist right, and all the fingers for the right hand. And then this is all the initialization, everything is initialized to 0. And then we plot this code is for B-spline approximation. So what I've done here is the input coordinates are actually taken input coordinates to the B-spline are taken, and these are plotted here using the plot function in MATLAB. So that code was to plot the centroid, and this is to plot a rectangle around the B-spline that we got. So the gesture output that we get so far would be different for different people because each person shows a gesture differently. So there is a need to normalize this B-spline. So that's why I've normalized this into a 100 by 100 frame. So this is the code for normalization, and I've plotted the normalized points and a rectangle around that normalized 100 by 100 frame. And then because we have a lot of points which are unnecessary, so there is a filtering that is required. So I have selected every 6th point in the trajectory, and those are actually given as selected L centroid X and L centroid Y. These selected points are then given into feature extraction. This is the code for global feature extraction from here. So what actually happens is that along the trajectory, we're trying to find out the wherever the points of slope change. So there is delta x1, x2, y1, y2. These are actually measuring if there is a change in slope. That's why I found out the tan theta values for these, and then I found out if the difference of this is less than some threshold that I've set. This threshold is set based on trial and error. So only the points that satisfy this criteria actually are plotted and I've plotted using the scatter function in MATLAB. And now I've plotted those selected points. And this code is basically to ensure that the number of maximum curvature points that we're getting is always 25 no matter what the gesture is. Because for any gesture input, we always need to get a fixed number of maximum curvature points, which are then used for processing. So I've got 25 points here as my maximum curvature points, these are taken as the global features. That is, global features account to the movement of the centroid, and then from now on we are going to talk about the local features, which is nothing but the movement of each of the fingers. So for the local features, I've plotted the B-spline for each of the fingers first, and then what I essentially do is I find the difference between each of the points on each of the fingers to the centroid, and then these are stored as the distance vectors. These distance vectors are actually they act as feature vectors for the local features. So now we have 25 global features, and then we have 30 local features corresponding to each gesture. So in total we have 55 feature vectors corresponding to each gesture. These are actually stored as the reference, and then any new incoming gesture is actually compared with these 55 feature vectors, and then we finally get the output. So okay, I'm gonna run the code and then show you the working. So this is the axis of least inertia, this is the 100 by 100 frame, and this is the line that is separating this frame into two parts. This is the trajectory of each of the fingers, that is the B-spline for each of the fingers. This is the box that I've plotted that was not normalized, and these are the feature vectors corresponding to each finger. This is these points are the chosen points, that is the 25 feature vectors. Those corresponding to each point. Okay, initially when I plot B-spline, this is the one that I'm getting, and then later on so this, as you can see, is not on a 100 by 100 frame. This is later on put into this box is actually taken and put into a 100 by 100 frame, and then we draw a line here, that is the axis of least inertia is here, and then I choose 25 points on these on the trajectory, and those are taken as the global features. Similarly, when I do the same, I find the distance vectors for the local features, and then in total I have 55 feature vectors, as I said before, and then these are taken as the reference, and then any new incoming sample is actually compared with these 55 feature vectors, and then we get the output as the recognized gesture. Okay, so in this code I'm going to explain how to recognize the features that we got in the final in the previous code. So I told you that we got 55 feature vectors corresponding to each gesture, out of which 30 were the local features and then 25 were the global features. So each of these are stored in each text file which I've loaded here. So corresponding to each gesture, I have taken 6 samples. The first sample is taken as the reference, second is taken as a good sample, 3 and 4 are taken as the average samples, and then 5 and 6 are taken as the bad samples. So by average and bad, I mean that while showing the gesture, we incorporated a little bit of noise so as to make the system more accurate. So these are the gestures that we took. One is accept, second one adolescent, then third is do, and fourth is see, and fifth is sphere, and then yeah. So each of these samples are loaded, and then we already found out the feature vectors in the previous code. So each of those for the first sample in each gesture, we take it as the reference sample, and for each incoming sample for each of the gestures, these are compared to the reference metrics that we have created, and then we predict the output. That's what is done in this code basically. So I'll just run the code and show the output. So this is the output that we can see here. 5 gestures were shown to the system in this order: accept, adolescent, do, see, and then sphere. So the gesture 1 is recognized as accept, 2 is recognized as adolescent, 3 is recognized as do, and 4th is actually recognized, it has to be recognized as C, but it is actually recognized as sphere. So there is a misclassification here, and then 5 is recognized correctly as sphere again. So these are the 5 gestures that we gave as input to the system, and this is our final output. These final outputs are then showed to the interface as a text.